Hi guys. Hello. Hey.
You're muted.
Hi.
Oh, am I muted? No, I'm not. Hear me?
Yeah. Yes.
Okay, excellent. All right. Let me keep going. I'm going to start by explaining a concept, and I just ran into a glitch, I have to admit, where some of the files that I had prepared were lost. So let me talk you through the concept. I'm going to have to rewrite some of the files in a bit. Let's see if we can still do that today. But before I do that, could somebody send back the third file that we created in class, because I accidentally overwrote it, and Zoom also doesn't allow me to re-download the original files. It stays linked to my original one. Here's good. So could somebody in the chat bring back the third file? Just send back the third file that I had before. Thank you, Navina. Let's get that back down. Download. Yes, great, thanks. So let me explain a concept to you first, and then I'll, because I think I'm going to have to shift a bit out of Grasshopper for the rest of the day until I have figured out how oh shit, come on, how I can solve my little scripting problem, which I promise you I will do. So let me just talk to you through the next level from this. So adding the diagonals is just a matter of figuring out the scripts to it. Here I see the script that I was missing. I was hoping to go through that with you right now. It's a data structure issue on how to actually identify the diagonals. Shouldn't be too difficult. There's nothing conceptually new there. So I'll sort that out and I'll get back to you probably tomorrow on this. I want to, once you have that, then another script that you can write is how to make your ties. I'll see if I can find that one as well. I can pass it on to you. But my data structure has been, my file structure has been messed up. So I'm sorry for not being sufficiently prepared. But why this matters, this is more a practical issue if you were to tie these structures together. So let me just explain it to you first as a principle. Like if you start with a square hinge, let me draw this up. In Bamboo, so if you make your base structure, oh, come on. There's nothing gonna work today. Draw. Okay, my annotation doesn't work anymore now. Okay, draw, okay. Fucking shit, nothing seems to work. Hold on, let me do that again. Screen one, annotate, yes, line, yes, okay. If you make your, no. Okay, it's gonna be one of those days.
You may try a whiteboard on Zoom.
Yeah, I'm opening it up now. Yeah, drawing on screen doesn't work. Like if you make your grid like this, say, and it deforms in, say, something like this, and you have your ties made, like the ties that you make, you don't want to lock in your joint. So typically what you can do is you can make a tie that would be, let me just draw two here. You can make a tie that ties around the bamboo like, that ties around the bamboo like this and like this. And then you're kind of locking in your joint. Like if you wrap it around it in both directions, it becomes rather stiff, which is dangerous because as you bend the bamboo grid, the wires may cut or may snap under the tension. So typically what you would do is you would tie it in one direction only so that you have a kind of a hinge in place. But what you see with this is that this tie connection allows these two edges to come closer to each other rather easily, but these two not. So because the material kind of sits in the way of it. So what you can do in the next script is basically analyze how your angles will change over time. Like say this angle here, angle alpha, eventually becomes a narrower angle over here. And the angle beta over here actually becomes a bigger angle over here. And this is a crucial piece of information to predict, because it will basically mean that if you work with bamboo, your ties, if they're wrongly placed, are going to cut or not. So what you should do is for, in the drawing here, angle alpha, you always need to keep the angle needs to always open up from where the tie is. So you need to connect it like this over here, and like this over here, and like this over here, and like this over here. Which means that in our grid system here, yeah, all the ties would basically need to be made like this. Now, throughout your system, from your flat grid, when it transforms from A to B, it doesn't uniformly transform. So it transitions from a diamond shape to a square and back to a different diamond shape. So somehow along in your system, you need to change the orientation of your ties. And that's good information to have ahead of time when you go in construction. So, and let me share back my screen again. What we did here is basically write a script that does that specifically, so you can start to see. Let me see if annotation works again. No? Oh, annotate is coming up. But you'll see that actually the tie direction is gradually. Do you still hear me? Hello?
The connection is a bit glitchy.
Yeah.
I mean, we can't see the screen. At least I can't see the screen. Your screen.
I can see the screen. I can't see it. It's black.
Hello? Yeah, I don't know what happened. Zoom just restarted by itself. Okay. Okay, now it looks like it's going better. Are you seeing my screen now?
Yes.
Okay, cool.
Yes.
So what you can see here in this deformed grid is that we have a transition going from diamonds in one direction to diamonds in the other direction. And that kind of requires that at one point, so here it's roughly around this line over here, that the tie direction needs to change as you keep on going forward. So that's not a very difficult thing to evaluate. You basically need to analyze your angles between your edges after your deformation, and then you need to identify whether the angle that you have becomes more or less than 90 degrees. And then with that, you can basically identify, fucking hell. Sorry, guys. No, it's not doing it. Oh, it's doing it. Okay. So with this simple angle evaluation, and I'll get you the script later down, you can basically map out on the flat grid how you need to tie it up so that as you build it up, the whole things don't snap. This is something that we figured out the hard way. It's a useful script to have. We'll develop, if it's not this days or this week, I'll make sure that you get it once I'm done with it. I have this, it is working. It's just that today nothing seems to be going fine. So we'll get around it. Okay, then there's a bunch of tools and techniques that you can use to, I don't know if you're familiar with Elefront, which is a very, very handy plugin because it allows you to tag and name geometry in Rhino as an attribute of each geometry. And with that, it's very straightforward to keep very close track of all your entire data structures and bake everything in a very coherent and detailed way. I'm not going to do an Elefront tutorial now. I'm just going to keep on going. Let's shift into this direction conceptually first. So with what we've just seen earlier, what I was mentioning is that there's a way to create singularities inside your equidistant grid. And for that, the way around it that we found works quite well is to actually work with diagrids. So I think it's Lunchbox that has a diagrid button that allows you to basically create diagonal grids. And why diagonal grids is because it automatically kind of resolves the continuity in the corners that you would have. So what we figured out is a pretty practical way of working and of designing for these types of structures is if you work with standard squares in the XYZ, well, sorry, perpendicular to the XYZ direction, so in the 3 orthogonal directions, and that you just model with those surfaces, and then you basically add or remove more red, green, or blue surfaces to your whole setup. And then all of these are subdivided diagonally in exactly the same resolution. And then all these curves produce interconnected curve networks. And then you'll see that you have these different singularities happening at different parts of the grid. So this is a triangle. Here you have a pentagon. Here you have a hexagon. And theoretically, you can keep on going as far as you want. But basically, anything more than a pentagonal shape here becomes kind of academic as an exercise, becomes kind of pointless because your oculus that you have in the middle becomes too big, become practically workable. So with this idea, in principle, and let me go back to the taxonomy that we're developing, you can create like quite a wide range of types of structures. So this is one with triangles, pentagons, and then here we're going to higher order structures. Now, what the problem is that if you keep this in totally abstract space, and the unit is say 1, then you can see that you get a bending radius in some of the tightest areas. And even with a triangular singularity, the bending radius at the tightest parts becomes a circle of 0.79 units, whatever it is that you're drawing in. And that becomes incredibly difficult to build with bamboo in its natural form. The most relaxed one of the singularities that you will find is actually the pentagonal one, where the radius remains at 1.38. And then for the other ones, it's actually with the hexagonal one, these become much more relaxed as well because the oculus becomes quite big. But an identification of the bending radius that you have in these parts becomes essential to evaluate whether or not your system is buildable. But why I'm bringing this up now is you can see that you can arrive at different types of shapes. So before, we were just working with a flat grid. And with that, you can just make pop-up shapes like this that you can distort in the form. So even in this one here at the bottom, there is no real singularity built in. In the Mannheim multihull, there's also no singularity really built in. There's some combinations here that don't really matter. But if you start to look at some of these other shapes, you can get to different geometries. So the triangulated one creates more of a pyramidal shaped dome structure. The pentagonal one allows you to bring in columns or allows you to delaminate from your structures. And then you see that the design solution space very quickly opens up quite a bit. The only challenge that we have is how to solve these geometries. So I don't know if I'll be able to open up Rhino again today. So let me just talk you through the scripts and the concepts, and then tomorrow I'll make sure I'm prepared better for tomorrow. Then we can go back into the scripting setup. So the way this works is you model basically with these 3 surfaces using the diagrid button from Lunchbox. It automatically produces the green lines that you see over here, and then we have a little data structure magic to make sure that we can separately isolate all the curves for the U or the X, the Y, and the Z direction. And then I've written this repetitive loop using Anemone. So Anemone allows you to write loops inside the Grasshopper environment, so your data can be brought back in on the other side. What we're basically doing here is we're looking through the orientation and the interconnectivity of curves. And what this script does is it will slowly join all the curves together that are touching each other. and then that becomes the input for your Rhino environment. Because to the script that was presented in the very beginning of the class by one of you, the biggest challenge is to always make sure that the interconnectivity of all the mesh, of all the line work is continuous. So that's what this script does. It basically interconnects everything in a looped, automated fashion. I'll make sure I can show you that tomorrow. And then that environment can then be brought back in a typical Kangaroo setting where you can bring in your anchors, where you can bring in, whatever you want to pull this thing to the ground. So here you see that from the original setup here on the left, we just pulled down the corner points on the anchors here, and already automatically it produces these trefoil symmetrical bending active shell structure, where all the anchors, all the edges are equidistant. So it's a very quick way to go ahead and build it. Now, the real challenge is in construction, how you actually would interconnect these grids. So that's what I showed you yesterday that we had done with an augmented reality test at CUHK when we made that one column that was going up. Around the singularities, it becomes very tense to actually connect the pieces together. There's a lot of forces happening there, so it becomes a construction challenge more than anything else. But in principle, this can be built using equidistant grid. Now, don't worry about this part. Now, one of the challenges, just as a concept to explain, to get your mind working, one of the things that we've done lately is, if this is the singularity, oh, let me change color. If this is the singularity in the middle, where the highest tension appears, it makes sense to actually extract that from our grid ahead of time and make this patch separately, because that's where the highest tension operates. And then to basically make all the other areas, prefabricate those flat on the ground and just connect them where there's low tension, and make the singularity as an individual freestanding element, and then connect the singularity to the base grid around it. And by that, you're kind of isolating the problem of the tension. And if you're doing that, then you can actually start to relax the curves in this singularity here. So right now, the reason why there's super high tension here is because everything is kept equidistant. But if only in this singularity you allow the equidistancy to be sacrificed or abandoned, and you do this with the layered method, with the tools that I showed you earlier, where we just intersect based on distances, then you can actually create these relaxation points around the singularities that can still be built with a bending active system without maintaining equidistancy here. So what that actually means is becomes kind of a hybrid system where the main grid here is entirely done equidistantly, but this part, the singularity, is done separately using interconnections that are not always at the same distance. And that piece would then be prefabricated separately. And that way of working has allowed us to, let me pull up the lecture from yesterday. I'll show it to you there. To make some of the nodes less intense. Let me clear my screen. While this is loading, let me keep on going here. Now, in all of these, of course, the bamboo thickness is something that has to be calculated for. We're not going to cover that in this week's workshop, but basically all the layers need to be offset as well based on the anticipated thickness of your bamboo when you're doing the marking up. So that's quite a challenging thing here, because you'll see that the layers change around the singularities sometimes, especially when you have odd numbered singularities. A layer that's on top may need to be forced to become a layer that's going underneath further down the line. But we're working on these tools to get, so here you see odd number sided singularities. We're working on these tools to find out how we can automate these parts. But the concepts are very similar. And then once you have that, then you can bring in the overlaps that we discussed yesterday verbally as well. You can offset each of your curves in the plane left and right using those the line dimensions that you may have. And then you can visualize them graphically by just putting some geometry on top of it, which is how we've been making our renders. But that's just a visualization tool. That's literally just putting circles on there with a certain diameter and then lofting in between them or blending in between them. Here you see on the bottom basically a strategy on how we could prefabricate the singularity first, and then all the other parts further down the line. Karamba tool, I'll talk to you about that in a bit. Let me show the slide that I mentioned. Oh, come on. Are you seeing my screen? Okay, now it's going. Okay. So in the model that we made here, around here, in this model, so here, in this one, we prefabricated singularities ahead of time. And you can see that there's no equidistancy here. Actually, the edge here is much bigger than the ones around it. And that's to kind of absorb for the sliding that we would have. So to build something like this, which is a drawing that is equidistant, that would actually be super difficult to make the singularities here. So when we did the physical study model, we actually started to relax the singularities already. So at the tip here, so this part, something like that, was prefabricated separately. And you'll see that the edge distance here is much less than the edge distances that we have there. But because of that, the bending radius becomes much less. And we can basically start to relax the whole structure. So that becomes the concept behind it. And that's why you see that the tip is quite rounded on top. It creates a more soft structure over here. Here on the left as well, you'll see the pentagonal singularity there. This one here, which has been prefabricated separately. So that's how we're going to have to build all of these in the future as well, which is quite a pain. It's not as easy to build these structures as it is to make a simple bubble pop-up structure, but it does work. It does work. Now I'm going to show you another quick talk that will build up on the rest. Oh, I'm not sharing my screen. Hold on 1 second. 1 second. Let me bring my screen back up. That starts to introduce the Karamba tools. So, yeah, in terms of all the analysis tools, some of them are very straightforward. To do a curvature analysis is very, very useful. And for that, you can just use the standard curvature analysis tools that you have in Rhino. So we have these simple tools that allow us to visualize where the curvature is highest. That's just a coloration tool, so there's nothing difficult there. But we have worked on something that I call the fingerprint tool. Let me open that lecture then. That's going to be easier to share. So this is a lecture. This is part of a paper that I did a few years ago for a conference on shell structures. And we ended up with a very peculiar situation. So during the construction of ZCB, I may have mentioned this, we're just using these standard bamboo species. I mentioned this yesterday, and the techniques that we have here in Hong Kong. When we were working with Arup to actually do the structural analysis of our whole pavilion, we just gave them the kangaroo outcome, and they sent it back to us with the answer that it works, which is quite surprising to us. But it was what they did is they just looked at the geometry. They took a value for the elasticity and the flexural strength of bamboo that they found in the literature, and then they brought it back to us and they said that it actually worked. But in reality, on site, we had seen that quite a few of the pipes, whenever we were bending them, they were starting to split and starting to break. So we started looking to that in a bit more detail. And this is a graph that we found in a paper from Julian Leonhardt, where he identified a whole series of materials that he said were actually good for using in bending active structures or even in kinetic structures. So what matters for those is the flexural strength and the Young's modulus, which is the elasticity modulus of a material. So metal has a much higher elasticity modulus than rubber or something like that, which would be on the left. And again, metal or carbon fiber will have a much higher strength capacity than wood. So what they said is bamboo actually situates itself over here, is actually a very suitable material to be used for even elastic kinetic structures. Western hemlock, which is material here, is what Fayotto used for the Mannheim Multihalle. So that one they said was actually not a very useful one. So when we started analyzing our ZCB bamboo pavilion, sorry, this is just background information that you've seen yesterday. This you've seen yesterday as well. What we started to see was that if we start to calculate the whole thing, looking at the curvature analysis, our very first calculations basically showed that our pavilion was failing, that it shouldn't have been possible to be built. And what we did is we looked at another source where they gave us the values of bamboo that we used, and it actually pointed in a very different location in the graph, but still somewhere that it should be useful. So this is the building code of Hong Kong, where there's a little bit of information on bamboo in a scientific report, actually, not in the building code, in a scientific report. So it said that there's a very different value than what Leonhardt was originally using. So what we did is we calculated our model with different wind load conditions specifically for Hong Kong, and we added initial strain. And what we found from the very beginning is that, that under it's, if you predicted the 2-year storm, that our pavilion would actually fail with 400% because the curvature of the bamboo was just way too high, which was a huge problem. It actually and yet we managed to build it in the end. So it was actually showing that our structure should not have been able to be built. So then we started to look into things in a bit more detail. And in Karamba, you can easily evaluate how the stresses run into a pipe that's being bent. So what we started to see is that in areas where the curvature of our pavilion was the highest, it should actually have been failing. And we did observe in reality on site that the bamboo was failing there. So what we had done to solve that problem on site is we took the bamboo poles, we cut little notches in them, we put a rebar inside, and then we put cement again on the inside. So we actually made a reinforced bent bamboo column around those parts to make it work. Now, there's an issue with the parameter assessment that we had. So normally, if you look at a fixed bamboo species with a certain diameter, then you can automatically identify, I'm a bit all over the place today, sorry for that. If you look at this slide here, this is a formula that shows you the tension, the maximum tension that you have inside your bent column. And the maximum tension is a derivative entirely of the diameter of your pipe, Z, and the radius of your bending, and then the elasticity modulus that you have. So for a fixed material, you can know exactly when the material will fail if you know the radius of the pipes and the diameter when you're going to at which you're going to be bending it, and that's a straight line. So basically,
sorry, could you just go back to that slide?
Yes.
Just want to register the formula. Could you repeat that again, please?
Yes. So the maximum tension that you have in your material is here on the outside. And that tension is entirely a derivative of the radius that you have and the diameter of your pipes here. I'm probably saying this again quite wrongly, but here you'll see the formula that this is the tension that you have at the bottom, the elasticity, the diameter of the pipes, and the inverse of the radius of your overall bending. So this is it's a linear relationship, and this curve here for a given bamboo species or for any type of material that you may have, basically says if you have a certain elasticity modulus E value and a certain strength Fy value, if your comb diameter is say 90 millimeter, then you can only bend your pipe until say around 11 millimeters. So for any material that you have, if you know the diameter that you have, you know how far you can bend it. And that's a linear progression that entirely depends on your elasticity value and your strength. So that's that actually allows you to evaluate your Rhino models very straightforwardly by just plotting out what your bending radius is. So what we started to do, this is all work in progress again, for any bamboo pavilion, you can basically discretize your entire pavilion and then map out the bending radius that you're working with. So here, for example, this is for a pavilion that we've mapped out all the bending radii, and you see that in some parts it's almost flat, but then in some parts in this particular pavilion, it starts to get bent quite a bit. So if you then map this onto your graph, then you can see, for example, that this whole area of the bamboo pavilion that you're working on cannot be built with the bamboo comb diameter of 90 millimeters, for example. This part of the pavilion should be built with a diameter, if you want to take this value into consideration, of actually only 1 centimeter. So where this becomes interesting is that it allows you to evaluate where inside your structure you need to work with thinner diameters or thicker diameters. And it's a direct data extraction from your digital models. There's nothing difficult about it. It's just discretizing your entire pavilion, identifying what the curvature radius is everywhere, and plotting it onto your graph that has your material properties. And then you can select your diameters based on it. So we kind of named this the fingerprint of the pavilion, because this signature is pavilion dependent. You can discretize it more or less. It will just make a smooth curve or a stepped curve. But this is kind of the fingerprint signature of each pavilion. And then we looked at a sample of bamboo species across the world that we could find. So yesterday I mentioned in Brazil, it's primarily guadua bamboo that's being used. Here we're using Philostachys pubescens or Mossos bamboo, which is in China. And we just looked up some of these values, and what we found out is that they differ quite a bit. Green means suitable for bending. And what we found out is that by chance, the Mossos bamboo that we were working with, if they're 1 year old, they're actually very, very suitable for bending. Or 3 years old, they're also quite suitable for bending. But other bamboo species like guadua bamboo is not elastic enough, or is not strong enough to be able to be used in a bent format, which is new information. So if you plot this out on this graph, where originally we said in the Hong Kong report, it says Philostachys pubescens is actually that one point. In reality, if you look at the range of it, it becomes a much wider zone on the graph itself here. So not all the species are useful for bending. And if you put that on the bending graph that I showed you earlier, then you see a very, very different picture again. So for example, all the Mosso bamboo species, even the ones with high diameter, say 15 centimeter diameter poles, you can bend them with a radius of 5 meters. But the guadua bamboo here, 3C, for example, only the ones with like a diameter of 1 centimeter can be bent at a radius of 5 meters. Well, that's a huge difference. It's a difference between like a finger or like a whole hand, like a fist thickness. So the bamboo species become super important in identifying which ones you want to use. And also the years start to become important, and the wetness of it. But nobody has done extensive research in this. We don't have the material science lab here to do a systematic research of all the bamboo species. But in principle, what this shows is that the bamboo that we have in Hong Kong or in China tends to be more, and in Japan, tends to be more suitable for the making of these types of bending structures. So if you just compare, we also identified there's a contradiction in different literatures. Like these are the same values. These are two values that we found in the literature for different species, radically different and radically different bendability. Or different ages also make some difference. or influence of humidity also plays a role. But it's the species more than anything else that makes a difference. So if we then start to look at the ZCB Bamboo Pavilion's fingerprint, it actually showed that we may have been quite lucky that we happen to have worked with a Moses bamboo of 3 years, rather than with the bamboo value that the government document had. And that's why our pavilion worked, except in a few parts where the pavilion, where the bamboo columns were kind of cracking. So yeah, ours was 3 years old, was working with these types of modules. And then if you bring those parameters into Karamba for your evaluation, then the pavilion shows much more realistic setup, that only in a few load case scenarios it would actually break, which is kind of what we have here. And these are the parts that on the pavilion we actually had to reinforce and fix back in the day. So what can we learn from this? With this graph, we can actually we can use this graph to identify where we want to use different diameters of bamboo. So say, for example, here we use 12 centimeters of bamboo for this part of the pavilion, 8 centimeters of bamboo for this pavilion, and maybe even 5 centimeters for the smaller parts. And that's one way to still realize your projects. And then this can very easily be brought into Kangaroo for the assessment. So the structures can be built safely if you want to. So we applied this just on a few tests here. Like if you would do it on a bubble like this, your fingerprint, the fingerprint of the pavilion looks like that. So that one would be a safe one to build with 9 centimeter diameter pipes. Yeah. So conclusion, you need to identify your species correctly. The model curvature profile of your pavilion can be used to identify where you want to use which types of diameters. You need to work with young bamboo for the construction, ideally, because that has a very good solution of it, and ideally also with wet bamboo rather than dry bamboo poles, which is important because typically in the market you'll find older dry bamboo poles rather than younger wet bamboo poles. So if you want to use it in bamboo construction, you need to work with that. And then within these large poles, you can select the top, middle, or bottom parts of the column sections where they have different diameters as well. So the bottom parts will be much thicker in diameter. And yeah, that's it. So why I'm bringing that up is because if I go to the next part, in the Karamba setups, I'm going to just quickly talk you through it here.
I have a question. Like, was there any deviation on site from the model you made?
Huge.
Huge.
Actually, I gave you a short version of the lecture yesterday.
Yes, yeah.
So after we built, let me pull it up while I'm talking. After we built the project, and hold on, give me a second. I'll pull up the slides in the meantime because I'm gonna have to.
And also, like, how major part did the labor cost? Because the structures we build here, the main problem is the labor. 80% of the cost is just labor.
Well, in principle, the labor force is not really a problem because the connection tie, as long as it's done well, as long as it doesn't start to slide, it's fine. So you just need to be able to make a proper connection, and then it's not difficult. So it's not a super highly skilled way of working. So we did bring in a bamboo specialist, and he in a very short time made sure that everybody who was working with us was capable of producing the correct knots. Hold on, I'm trying to opening the okay, it's coming up. Yeah, it's coming up. Then everybody was able to make the correct knots. And then that's fine. So the labor force, in principle, if you do it well, it shouldn't be a big problem. The deviation, though, that was a big issue. Let me show you something that I didn't show yesterday. Let me go here. So when we prepared the fabric, the first time we put the fabric up, they unrolled it and they discovered that it actually was put on wrong. Orientation was off. So here you see the long leg on one end being overcovered and this one not being covered. And this was a huge problem because this is like draping an iron stocking over a rose bush. There's no way you're going to be able to just pull it off again without destroying the fabric or destroying the bamboo structure itself. So we had to very carefully roll the structure off. But a problem appeared, like as we were facing the situation here, all of a sudden the skies turned black and a black rainstorm came in. And a black rainstorm in Hong Kong means that you have more than 7 centimeters of water on a flat surface per hour, which is huge. And this is a curved surface, meaning that the water started to converge in certain parts. So all of a sudden, these massive water bubbles were forming on site. And this is about 2 cubic square meters. So this is about the weight of a Mercedes-Benz that's hanging from a grass structure. So immediately the craftsmen on site, they ran up and started stabbing the fabric to let the water out. And they started to push the fabric, to push the water out. And we had a bit of damage on it on site. But luckily, we're then able to create these temporary supports to prevent the water from going in. And then we had to take off the fabric the next day. And as I mentioned, you need to kind of roll up the fabric very carefully. So we did that. That worked out quite well. But then while they were doing that, all of a sudden the wind direction changed, or they hadn't checked the wind, and it started to blow inside the structure. And all of a sudden this whole fabric started to take off. And it was only hanging for a split second on one point on the crane. And then it crashed down onto the pavilion, impaling itself, causing more damage. And then we had to fix that. But then the second time we did it, we fixed everything. We patched it up. We made sure the orientation was correct. And then, we managed to sort out, fix the fabric, and then everything worked out. So once everything was built, and I hope I have the scan here. Yes, I do. Let me first show you this one. We did scan, so we made some large-scale physical models ahead of time. Do I have those here? I don't have that diagram here. No, I don't have the diagram here. But I do have the scan of the final pavilion, and then we compared that with the original. And you see that in 2 parts, the blue areas, the deviation was actually more than 1 meter. So we were a meter below the original roof height that we need to have. And we thought for a second that that was maybe because of those water bubbles that had taken place there. But those were actually more on the left here, where there was not that much deviation. So the bamboo was actually able to take the weight. What we think happened here is that 2 of the 3 directions are almost straight. And we think that the bamboo just straightened itself out completely, basically flattening out the structure. But luckily, the synclasticity was maintained. So the challenge was that as long as the structure is deforming like this, it remains strong. But the minute it would deform like this, for example, then it becomes super weak. Or the minute it would start to do something like this, then it becomes super dangerous. Because then as it creeps and deforms, it becomes weaker and weaker. And luckily, the deviation here was such that it flattened out things a little bit, but it did maintain its synclasticity. It was never bending down the other way, and therefore the pavilion was never into any risk of deforming further. Yeah. Let me go back to the Karamba file. Just give you an introduction on the concepts here, and then later on we can look at the scripts in greater detail in the coming 2 days. So in Karamba, what you have is you basically have just, are you familiar with Karamba? Is anybody familiar with Karamba?
Yeah, just a little bit.
Yeah, so Karamba is basically a structural analysis tool that allows you to run a finite element analysis over it. And there's a little bit of a similarity maybe in concept to Kangaroo, but it's very different. So what you do is you bring in your geometry, and then you assign material values to it, and then you put in a load condition. And the software will produce a finite element analysis of the whole thing, and it will give you the outcome of it. So the trick is to really produce a precise model where all the points intersect with each other properly, and that you have all the hinges and all the movements very carefully defined. And then you need to apply all your material constraints to it. So let me first see if I have a quick image here. Yeah, so this is an image here on the top left, where you see that what we're creating is actually a setup that's abstracted, but where these rings mean that the geometries can hinge around each other completely. They're never welded or fused together, which is different from a steel space frame. Because if they're linked together, like in a Vierendale truss, then it becomes a very, very rigid connections. These all have to continue to be very, very loose connections in your geometry setup. So, so yeah, let me just talk you through the main elements that you have in Karamba. So you have your input setup, then you have your assembly and analysis tools, and then at the end you have your visualization tools that basically show the outcomes of what you're working with here. So there's elements that turn lines into beams, where you just put in line geometry and automatically it turns into a beam. You need to give the properties of those beams, like the type of sections that you're working with. So here we're working with it's a bit low resolution, but we're working with a circular cross section with a diameter of 8 centimeters and a wall thickness of 1. That's the standard pipe diameter that we're working with. This is every object has its own identity number as well. So that's where the Elefront plugin comes in quite handily if you want to separate your beams into different branches with different properties, like different diameters. Karamba really relies on a very clean data structure to assign all the properties well. Then the foundations that you define over here. So you see that all the points on the ground are locked in the X, Y, Z, and in the rotation directions. That's something that's debatable, because we locked everything in because we're anchoring the bamboo quite rigidly in the ground with those steel elements, the steel rebar that's cast inside the bamboo. Then there's the loads that you need to bring in. So we have a few loads that work together. There's the self-weight, which is purely a gravitational setup. It's just based on the weight and the volume of your material. Then there's the initial strain, which was a new component that the Karamba developers wrote for us, where basically, depending on the bending radius, which is what I was just showing you earlier in the slideshow, there's a pre-strain in the material. If a material is bent quite a bit, there's already tension on the outer fibers of your material, on top of which self-weight and wind loads are added. So sometimes the self-weight or the wind load can neutralize the initial strain, but sometimes it's just added on top of it. So that's a very dangerous part. If you calculate bending structures without the initial strain, then you really risk arriving at an overly simplified model, which I think is what happened when Arup did the calculations for us, that it didn't include the initial strain. I'm not 100% sure of that, because otherwise I'd be very surprised that with the values that they were working with, that they actually approved the structure, because it's the initial strain inclusion that all of a sudden showed that we're totally off. And then there's the wind loads as well, which, as I mentioned in the lecture yesterday, is the main thing. So in the Hong Kong Building Code, there is a formula that you can find that defines how much wind load you need to work with, and that's based on the surface area, the mesh of the mesh that's covering the pavilion. That's what catches the wind. So the input here is the surface itself, and then different vectors with different safety coefficients. So, for example, the wind load that we needed to work with is 2.05. I think it's Pascal or kilopascal, I'm not even sure now. But then there's safety factors that can be added, depends on whether or not you're working for a 2-year storm or a 5-year storm. The lifespan of the pavilion also plays a role. So every part of the world has its own wind factors that you need to bring in. And those are just added into the pavilion. And then we have the joints. So here, that's what I mentioned, that all the connections are actually loose joints. Yeah, and then at the very bottom, we have the material setup. So here, that's where I mentioned that there's different materials and different families that you can easily bring in. So you can just bring in the Young modulus and the strength of the material as a parameter in here. So it's very easy to shift between from bamboo to steel to aluminum. It's the same digital setup. It's just different parameters that are brought in here, and then you will have a fully rigid, fully solid scientific calculation of the structural performance. And then what Karamba then does as an outcome, it gives you basically a visualization of the color, a color visualization, where it shows you the strain, where 100% is when you're above or below the maximum or the minimum strain. So there's nothing new there. Like, these are pretty standard Karamba buttons that we've just applied. The initial strain is a new one that they added for us. I think it's part of the general Karamba plugins later down the line. So what we did is, basically test out different bamboo species with different diameters and different properties. And then you can very easily swap between them to identify what material you want to be working with. That's it basically. And then this idea of the curvature graph that I mentioned earlier. Yeah, it's all a bit in a messy state. This document still, where this is what I was mentioning earlier, that it's still all work in progress. And then we did this test on the Taiwan Pavilion that I just showed you earlier, trying to also identify what the resulting foundational force is that you need to have. So if each of these slabs or if each of these bases are a concrete slab that need to keep the pavilion from taking off when wind is blowing at it, you can basically take an average of a summation of all the resulting vector forces at your foundation, and then you just need to make sure that your concrete is heavier than that. So yeah, those are some of the tools that I'm hoping to be able to show to you tomorrow and on Friday. And I do have to apologize for the glitches that I've been experiencing today. But yeah, any questions?
Yes.
Yeah, go ahead.
The Karamba bit.
Yeah.
Did you use the? Okay, so just hold it over here. You have a base network, a curve network, which is derived, and then you said that there are other operations we do where you give the offsets for the radius and then overlaps of the bamboo. So what model or what line network was given for Karamba analysis? Was it just the base mesh, or was it the mesh which had all the overlaps and the offsets?
We have experimented with different things, and the solution that we found that works is that if you have two bamboo poles that are crossing each other, that you actually, what we did is we added a tiny steel member in between it, a little steel pipe. Oh, I rotate. We simulated a little steel pipe, a little steel ring in the middle here to space these out. And then we basically had a hinge over here and a hinge over here. And that was kind of the compromise that allowed us to create a fully hinging setup higher up, because normally it's difficult to create that in a Karamba setting. But this way, we managed to work our way around that. And this allowed, and then the hinges, these steel pipes, they don't really contribute to the overall strength. They're just like a centimeter thick or 5 centimeters thick. It's just literally a placeholder in the overall calculation. But this is something that allowed us to work our way around this.
Okay.
And it's something that we could easily do, because to do the fabrication drawings, there you need to have everything nicely spaced out. There you need to work with all the offsets of all the layers in a clear way.
Okay.
Yeah.
My next question is to actually get those difficult bends which kind of go beyond the range of the radius and the have you tried heat bending, or is it something that you'll be trying? Heat
bending works. Heat bending is good. It's something that's applied a lot. We were trying to prevent it just to keep things simple, because heat bending is really a tricky thing. We've worked on heat bending with Hong Kong scaffolders, and they absolutely failed at it. It's a real craft. That's something where skill really comes in. Because the bamboo humidity needs to be sufficient enough. Typically, the bamboos that we get here are rather dry, and to heat bend those is really difficult. Because what you're actually doing is you're by adding heat with a blowtorch, you're kind of steam bending it, right? The heat evaporates on the inside, it becomes kind of supple. So yes, it's possible. It was not possible in the Hong Kong context, but that's a very good way to do it. So that's another thing, depending on where you're working. If you want to prefabricate your singularities, you can pre-bend your, like you can abstract, like the curvature is always three-dimensional, but you can abstract it to a plane and pre-bend it in that shape already, so that there's much less resistance as you're assembling it. So that's definitely a way to speed up the production. Yes, definitely.
So I'm just going to ask one more question.
Sure, sure.
I seem to be taking up all the
time.
No,
thanks. I'm happy that you're into it. Thanks.
Yeah. My next question is, how do you decide which diagonal to choose to anchor in a quad?
Which diagonal to choose?
Yeah.
Let me go back to some examples here. Hold on. Let me share screen. Are you seeing this?
Yes.
So currently here, we just had, so you can indeed flip between two directions, basically. The thing is that around the singularities, especially if you have odd numbered singularities, then it doesn't become super clean. So here, but this is a hexagon on top. So here it's very easy. You can either pick the U direction or the V direction. It doesn't matter. You don't even need all of them. You can get away with just a few. Like if you would look at the Mannheim Multihalle, and let me see if I have an image of that right at hand. Hold on, let me see. I may have one here. Hold on. In the Mannheim Multihalle, they put metal wires through it. They actually didn't. Come on. Yeah, here I have a few more images. That's the Mannheim Multihalle. What they did is, it's a bit hard to see here. Here you see it nicely. You see the gray lines on top? Those are the diagonals that they added. So they only did it like every 10 cells. And they did it with a metal wire, because that's what's taking all the tension. Like if you can identify, and there's a good point there. So each diamond shape that you have can change under its natural weight. And there's two directions where it can change. It can either become more square, or it can become more diamond shape. And if you work with steel tension cables, if you're in a scenario where it tends to go into that direction, then you want to add your tension cable over here. If it's in a scenario where it wants to go into this direction, then you want to add your tension cable here, because you always want to put it on the line, if it's metal, where it wants to lengthen out, because the cable works in tension. If it's under compression, it will just become floppy, basically. So I don't know how they defined this in Fayotto's thing here. My guess is that they just arbitrarily applied it every 15 cells or something, and they just put metal cables all the way through it, loosely connected, and then they tightened those. So if you look at the next slide, I hope it's in here. No. Okay, I don't have the clear photos here. But what they basically did is, these are two cables. You can see it a little bit. What they did as a tension mechanism, so they put two cables through it, and then they put a spacer in between it. And what they did is, with those spacers, they would, if you had two cables, oh, I'm drawing poorly. Let me draw clearly. So you had two cables. They would put a spacer here and a tie over here. And this spacer basically allowed them to push the cables further away from each other. With kind of a screw spacer in here. And that's a quick way that they use to locally be able to tighten the cables wherever they needed to. So it's a very clever system that I'm pretty sure they just figured out on site. Because I don't know if you would be able to get that information, or maybe you would, from models like this. Maybe you might. But you can definitely see from the flat grid where you're arriving at. Yeah, so the angle of diagonalization is a choice.
There is no analysis which kind of helps us understand which is the right diagonal, because there are many ways, and depending on the logic that you just mentioned about where the quad will tend to move, whether towards a square or a diamond, so, you may want to change the direction of diagonal through the structure based on.
Yes, well, ideally, it depends on the element that you're using to make diagonal. If it's compression or tension, bamboo actually does both. It's not going to buckle in the small distances that you have. So if the material is a rod-based system, then it actually can do both. So what we did here, let me zoom in a little bit. You can see it. We added a few diagonals in a logical setup. So I don't know if you can see them. There's one here, 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 and then here, 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 and then on the other side as well. And they're just coming, what we did is we just took the verticals from the legs and then we extended those, because that gave quite it's an aesthetic solution, it's an easy solution, it's a logic solution. And the biggest loads that we had, the biggest deformations were actually around the legs. So by solidifying those parts, it actually worked out quite well. And also the radius of these verticals was much, 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 much less than if we would put rings here in bamboo, which would be impossible. So it's both of these considerations together that were brought into the equation.
Thank you.
Yeah.
I have a question again.
You're asking all the right questions. Okay. It's good.
So, like when we talk about heat bending, so does it affect the bamboo, and how do you consider it in your structure while you're working digitally?
So when you talk about what, cane bending?
Heat bending.
Oh, heat bending. So heat bending, what it basically does is it takes away the initial strain. So it's basically plastic deformation. So it's like if you have a metal pipe and you bend it beyond its plastic deformation, then it stays in that shape. So that means that in your Karamba calculation, you can just remove the initial strain component here, which is a major one for high bending pavilions. But heat bending, I mean, it adds again carbon to the whole project as well. So if you can do it without, then that's fine. But it's definitely an easy way to solve the problem.
And just out of context, do you use nut bolting there?
Say that again?
Nut bolting, drilling and using nut bolt.
The problem with bolting is that the bamboo can split easily. So with bolting, you need to be a little bit careful as well.
Okay, and one more thing, like you mentioned the rings. So did you use any additional frames or structure for the pavilion while executing?
For this one?
Like while executing the pavilion on site, did you use any external members to strengthen the shape or form or anything?
Well, we had the temporary scaffolding underneath it. We had this.
Not the scaffolding, but any permanent ring or anything you had to add to keep the members in particular form?
No, we pulled them up on site in a straight fashion. So it was literally like, it was like this. They're straight. And we hoist them up, and we just bend them. We just bend them on site. And then we just pull them into position. That's it. Yeah, we marked up a little bit on the scaffolding where they needed to be, and we used the scaffolding to anchor a few of them. That we did, but not much more than that. Yeah. Okay. Any other questions?
Just like wondering, like when I look at the Golden Moon project, how just the bamboo just became more structural. I'm wondering why couldn't you achieve the sphere shape with bamboo, or like I'm just wondering why did you use steel in the first project and then the bamboo became more structural?
We use steel because steel is coded in the building code. Without steel, we couldn't pass through the building code. So for the ZZB bamboo pavilion, the only thing that was approved by the building department was the concrete foundation. On the upper part, the bamboo master, the structural engineer, and the authorized person that signed off on it took personal liability for the whole project. without a building code to fall back on. So if this pavilion would have collapsed, they would have been in jail. So they took a huge risk. So we found the right people to help out with this. So that's what I meant when I later on, when we continued to work and we set up this Karamba workflow and we saw that it should actually fail, we kind of flipped out because everybody thought that Arab said, go, we're good to go. And then our own calculations, and we're not structural engineers, we're just architects playing around with these tools, but point out an impossibility almost. And then it looked like that we were just lucky with the materials that we had, that it kind of worked out. So there's a big, big problem. If there's no building code to fall back on, then I guess it's difficult.
Okay, interesting. I was curious. Yeah.
Guys, I apologize a bit for the chaotic nature of the scripts today. If we can maybe wrap up a little bit earlier now, and then tomorrow morning we can pick up again. And what I'll try to do is I'll try to immediately jump to the fun part, or the second fun part, which is this part here with the singularities, because that's something fun that we can play around with. It's nice to see how you can design with that. I don't know if we'll need to rewrite the whole script. Maybe I'll just explain it briefly, but I'll make sure that we have this in place with this loop thing working. And then we can start designing a few of these structures. We can play around with that. I'll make sure that we have that ready by tomorrow, first thing in the morning, and then we can go ahead. Does that work? Okay. All right. Well, then let's cut it 15 minutes short, and then I'll see everybody in the morning tomorrow.
Thank you.
All right. Thanks, guys.
Thank you.
Thank you.
Bye.
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 Thank you.